Hello and welcome to this lecture. In this lecture, we will start our study of solving linear equations. Okay, and once again, we'll use our same principle. We'll start with the simplest possible cases where we immediately know what the answers are and then try and build up from there. Okay, so two linear equations in two variables is what we are starting with. Of course, you will say you can start with one linear equation in one variable that we have seen before, right? So even in some previous lecture, we saw how if you have one linear equation in one variable, you can solve it, right? Some ax plus b equals c, you know how to do it. You take b to the other side, divide by a, you get usually you get one solution and you can write it down. It's very easy. One equation, one variable, one linear equation, one variable. I'm not going into detail. I think you know how to do it. You'll see it will show up here in this case. Okay. The next simplest case is two linear equations in two variables. Okay. I will use this as an example to illustrate various things, various different ways of viewing this problem. And you will see some of these ideas are important, and how you visualize the solution to linear equations is important. So pay attention. The technique itself might be very simple here, but you know the way of viewing the solution will be different, and that is something that you have to pay attention to. Okay, so let's get started. Okay. So what is going to be my notation for the two equations in two variables? I'm going to use this notation. We may change this notation later on, but it's just a starting point for a good notation. So I'll say a1x plus b1y equals c1, and then a2x plus b2y equals c2. Okay. So depending on the values of ai, bi, ci, clearly different types of solutions are possible. So now you have to keep in mind some obscure cases that can happen, right? So let me just talk about them immediately and then get rid of it so that you don't have to worry about it later. For instance, all of the AIs and BIs and CIs may be zero. This zero is you'll see it's one borderline case where you have to be slightly careful about making statements when zero is involved. So if all of them are zero, what does it mean? It's 0 equals 0, 0 equals 0. There's nothing to solve. Any x and any y is good enough, right? So you can take anything. So 0 equals 0, 0 equals 0. So those kind of corner cases will always be there. For instance, the other corner case is a1 equals 0, a2 equals 0. So such cases where x will disappear or y will disappear or both x and y will disappear because of that. Or you may have another crazy case where a1 is 0, b1 is 0, but c1 is not 0. What does that mean? Right? There is no way you can make that equation work. Okay, so I want to briefly comment on these corner cases and tell you that don't worry about those corner cases too much. They will come and affect you a little bit. You should be aware of them, but don't bother about them. So typical cases, you can think all of them are non-zero, etc. And to begin with, okay, don't get too complicated, too confused by that. But nevertheless, I want to definitely motivate the fact that depending on the values of AI and BI and CI, all types of different solutions occur, right? And to visualize these linear equations, at least in two variables, two linear equations, you can very easily visualize. When there are two variables, there are easy visualizations. You can have a graphical way to visualize it, right? So these are nothing but two straight lines, isn't it? And then we already saw that the graphical solution has this limitation that scaling and all becomes an issue. You have to zoom in, zoom out. It doesn't work that well. It turns out algebraically there is a wonderful method called elimination. Okay, it's very, very important to pay attention to that. And finally, the solutions for these linear equations are typically, in fact, even this linear equation itself is written in this matrix vector language. You think of things as vectors and you think of things as linear equations as linear combinations, and you write down the answer as a linear combination of vectors. Okay, so all these three views are very, very important. You have to get comfortable with this kind of a view of linear equations, the graphical view. Of course, when the number of equations become very large, the graph is something that you cannot draw, but you can still visualize. Graphical view is sort of important. The algebraic view is extremely important. It's the most useful in actually numerically solving the problem. And then finally, this matrix vector view is important to understand the nature of the solution. You get a solution. What type of solution is it? Does it satisfy some properties? Can I do something more with it? So these kind of things are possible in the matrix vector description. Okay, so we'll try and address all three in this particular case because it's very easy to easy case to deal with. But then we'll slowly generalize. As we generalize, pay attention to these things. All these three are very interesting. Okay, let's begin with the graphical view. Okay, so it's very clear that a1x plus b1y plus c equals c1 is one straight line. a2x plus b2y plus equals c2 is another straight line, and these two straight lines can be of different forms. They may intersect at exactly one point, which is what I've shown in this picture here, right? They may intersect at exactly one point. They may not intersect at all. They may be parallel, depending on the value of a1, b1, c1, a2, b2, c2. These two may be parallel. They don't intersect at all. Or both of them may lie completely on top of each other. Both the lines may actually be identical. Okay, can this happen? I'll show you some examples, right? Again, just a1, b1, c1, a2, b2, c2, right? So if they satisfy some conditions, it turns out you don't really have two lines, you have only one line, right? One on top of the other. So in each of these three cases, which you can easily visualize graphically, it turns out the type of solution is very different. When it intersects at one point, there is a unique solution. There's only one solution, exactly one solution to the two linear equations. When they are parallel, there are no solutions. No value of x and y can simultaneously satisfy both those equations. If both lines are identical, there are infinitely many solutions. Okay, it's any x has a corresponding y, right? That's what happens when the two lines are the same. Okay, there are three types of solutions, and the question is how to determine which one actually applies for your actual problem, right? So graphically you can do it, but we've always said that graphs may not be the exact way to do some things. We also want an analytical procedure. Okay, but I want you to keep this graphical notion in mind. It will sort of help you to visualize how these equations are working out in practice. Okay, so that's something important. But the next process that we're going to study, the analytical method, is extremely critical. That's what will help you solve the problem. How do you determine which one of these things are actually hold in your problem? Okay. Once again, to do that, to solve the system of linear equation analytically, we'll start with various easy cases. Very simple, trivial cases, how to solve them. And you'll see the solution will be very immediate in these easy cases. And then we will follow the approach of taking the general case and trying to simplify it to the easy case. Okay, you remember a solution of quadratic equation, right? That's what we did. We started with easy cases, and then suddenly we found the most general case is also the same as the easy case. Okay, something like that we'll do here. Okay, so there's one particular easy case which I will call as triangular case. It's I'll tell you why it's triangular a little bit later, but I'll call it the triangular case with a non-zero diagonal. Okay, so why all these things? It comes from the sort of the matrix language, and we'll see that later. Okay, so that corresponds to this particular case I've shown here. Basically, a2 is 0, a2 equals 0, and then a1 and b2 are not 0. So this a1 and b2 are basically one diagonal in my equation. You can see it's on the diagonal, right? So a1 is not 0, b2 is not 0, but a2 is 0. So when a2 is 0, you sort of get a triangle here, right? Do you see this triangle? This is the triangle I'm talking about, right? If a2 is not 0, you get a square, no? The matrix is like a square. And then when a2 is 0, this part is gone, so you get a triangle. So that's the sort of triangle picture. Let me just remove the triangle away. You can sort of see where the triangle is coming from and why the diagonal is non-zero. The diagonal part is non-zero. So a1 is not 0, b2 is not 0. So this case, it turns out, is a very easy case to solve. Why is that? Because look at the second equation. That's only one variable, one equation, right? So you know immediately what the solution is. Y is c2 by b2, right? Easy. Once you found y, the first equation also becomes one variable, one equation. So you put y equals c2 by b2, push the B1 C2 by B2 to the other side, divide by A1, and you get x equals C1 minus B1 C2 by B2 by A1. Okay, so you get a unique solution in this case. Okay, very easy case. Triangular non-zero diagonal, extremely easy to write down the solution. Okay, now this non-zero diagonal stuff, I'll comment on it real quick. But before that, we'll see two easy cases. What is so special about non-zero, right? That's the part I want to comment about. Even if it is zero, it's not too much of a problem, right? Notice what happens here. There is this one variable case where both A1 and A2 becomes 0. Supposing both A1 and A2 are 0, it's like you have two equations with only one variable y. So if you want any sort of solution, you should have C1 by B1 to be equal to C2 by B2, right? If C1 by B1 is not equal to C2 by B2, then there is no solution at all. There will be no one y which will ever satisfy this. X doesn't matter, right? X can be anything. Any value of x, you're okay. X could be 10, 20,000, 1.0. Doesn't matter. X doesn't even enter the equation. Okay, any value of x is okay. But to have some value of y satisfy both equations, you want the ratio C1 by B1 and C2 by B2 to be equal. If they are not equal, then you won't have any solution for this system of linear equation. This is a very simple system of linear equation. So all x and C1 by B1 equals C2 by B2, then you get infinitely many solutions. Now there is this all sorts of concerns about what if B1 is 0, what if B2 is 0, etc. You can derive those cases. For instance, if B1 is 0 and you receive C1 is 0, it's okay. You can deal with those cases very easily. Another way to write this condition is, instead of writing it as a ratio, you can cross multiply. You can write B2 C1 equals B1 C2. Okay, that's the way to cross multiply and write it. That way you don't have this division. But anyway, even if you divide by 0, you imagine the cross multiplication to hold. Okay, don't go too much into this 0 situation. When it happens, we'll deal with it in some examples. Okay, so the one variable case is also a trivial case, easy case to deal with. You either have no solution or you have infinitely many solutions. Okay, another case which is equally intriguing is the one equation case. You don't really have two equations, you have only one equation. A2, B2, C2 becomes 0. What is A1x plus B1y equals C1? There's only one equation involving two variables, linear equation, and that is a straight line, right? So you have infinitely many solutions. Any xy on that line, A1x plus B1y plus equals C1, is a valid solution to this one equation. So let me quickly summarize the slide. The most non-trivial important part of the slide is the triangular non-zero diagonal case. The triangular non-zero diagonal case is extremely important. We're able to see that there is a unique solution in that case. The other two trivial cases are one variable and one equation, and they seem to result in this crazy situation of either there is no solution or infinitely many solutions. Okay, but nevertheless, you see that even in the easy cases, these three possibilities are occurring again. The unique solution, one solution, no solution, the parallel sort of case, and infinitely many solutions, right? So easy cases are also plentiful in the type of solution in some sense, right? So you have infinitely many solutions in some case, you have no solutions in some case, you have a unique solution in some case. Okay, so linear equations, even though they seem very simple, can give you very many different interesting answers. Okay, so these are the easy cases. What do you do for the general case? Okay, so in the general case, you can use the simple technique called elimination to get rid of one variable. Okay, in some sense, you can find an equation that has only one variable. Okay, you get rid of the other one. Okay, how do you do that? That's called elimination. Elimination is getting rid of something. So you get rid of one variable, you eliminate one variable from the two equations. How do you do it? Some of the cases here are very, very easy, right? Already one variable is gone. Like for instance, if A2 alone is 0, you again have gone back to one of the easy cases. If A1 is 0, again you've gone back to one of the easy cases. If A1 is 0, it looks like some other triangle, but you can move the equation around, right? You can move this equation around. And there's a bit of a typo here. This should be 1. Okay, it's not C2. Okay. So this second case, if a1 is 0, you can reorder the equation. You put the second equation first, put the first equation second, you get back into your nice little triangle type situation. So both these cases are very easy. If either a2 is 0 or a1 is 0, you already have one variable out, right? One variable has been eliminated. So it's very easy to do it. What if both are not 0? If a1 is not 0, a2 is not 0, then you can eliminate to make it look once again like a triangle case. How do I eliminate? This is where the very interesting idea comes in. Instead of equation 2, you replace it with equation 2 minus a2 by a1 equation 1. So let me just show this here. I have a1x plus b1y equals c1, and then a2x plus b2y equals c2. I'm going to multiply this equation by a2 by a1. So what is the meaning of multiplying this equation by a2 by a1? Both the left hand side and the right hand side I multiply by a2 by a1. Okay. So if I do that, what will I get? a2 by a1 times a1x plus a2 by a1 times b1y equals a2 by a1 times c1. So here I'm going to get these two to cancel, and I will end up getting this wonderful looking equation a2x plus b1 a2 by a1y equals c1 a2 by a1. Okay, so this is also a linear equation, but notice these two linear equations, they have the same a2 here. Now I'll take this equation and subtract this guy from it. Okay, so I'm going to get, if I subtract a2x plus b1 a2 by a1y minus a2x minus b2y equals, or let me subtract the other way around. Maybe that's how I've written it here. So let me just subtract the other way around. So what is the other way around subtraction? a2x plus b2y minus this guy equals c2 minus c1 a2 by a1, right? So I've subtracted this equation and this equation. Okay, subtracted this minus this, I'm going to get 0. Interestingly, now notice what happens. a2x here, and they get eliminated. So x gets cancelled out of this, and you only have y, and what do you have? b2 minus b1 a2 by a1 multiplied by y. So I can take y common out here. I'll get c2 minus c1 a2 by a1. So this step of eliminating is at the heart of analytically solving linear equations. It's a very simple sounding idea at some level, okay, but it's extremely important and very crucial in being able to solve linear equations. Okay, so let me go back here. Basically, I'm replacing equation 2 by equation 2 minus a2 by a1 into equation 1, and just like I showed you, I end up with two equations now. The first equation is as it is. I'm not replacing it with anything. a1x plus b1y equals c1. Guess what the second equation is? Second equation is got just one variable in it. X is gone. I have b2 minus a2 b1 by a1y equals c2 minus a2 c1 by a1. Okay. So that now is again an easy case. So you see whether a2 is 0 or a1 is 0 or both are non-zero, I can go back to the easy case which has this triangular form, and I know how to solve this case, right? One can easily figure out solutions for this. Okay, once again, you saw how we proceeded. We started with some easy cases where we can quickly figure out the solution, and then we looked at the general case and tried to get to the easy case in some way, and that method is elimination. Elimination is the most important and interesting idea here, and that gives you a very easy way to solve two equations, two variables, two linear equations, two variables. Okay, so let's see a bunch of examples. There are like 4 examples here. I want to quickly go through each one of them. The first one is x plus y equals 1, x plus 2y equals 3. Okay, so let's start with that. The first one, x plus y equals 1, x plus 2y equals 3. Let me just make sure I got that right. Okay, so what do I do here? I see that both these, this is in the square form, it's not in a triangular form. I have to do elimination, and for elimination, this is equation 1, this is equation 2. I'm going to do, instead of 2, I'm going to replace 2 minus 1, right? A1 is 1, A2 is 1, so I'll have to do, if you want, I'll do it in gory detail. A2 is 1, A1 is 1, which is the same as 2 minus 1. And what will this 2 minus 1 be? X plus 2y minus x plus y equals 3 minus 1, isn't it? So x is going to cancel, 2y minus y is y equals 2. Wow, I already got y equals 2. So you put y equals 2 here, I'm going to get x equals x plus 2 equals 1, which is x equals minus 1. That's it. I've solved. Anytime you get a solution like this, there is a unique solution, right? So unique solution to minus 1 comma 2. Okay, so you can go back and check this, do a quick check, right? Minus 1 plus 2 equals 1, minus 1 plus 2 into 2 equals 3. Both are checked, you're done. Okay, it's a very, very quick way to solve a system of linear equation, and you saw how I did the elimination step, and the elimination step directly gave me a unique answer, and I was done. Okay, let's do one more. 2x plus 3y equals 5, 3x plus 4y equals 7. Okay, so this is 1, this is 2, and quickly I see that a1 is 2 and a2 is 3, right? And my elimination is going to require 2 minus 3 by 2 times 1, right? Which is going to be 3x plus 4y minus 3 by 2 times 2x plus 3y equals 7 minus 3 by 2 times 5. So notice here I have to multiply the first equation by 3 by 2 and then subtract second equation from the first equation. I'm doing both of those together. If you want, you can do the multiplication separately and then do the subtraction. So if you do this, 3x will cancel. I'm going to get 4y, 4 minus 9 by 2 y equals 7 minus 15 by 2. So if you solve this, I'm going to get y equals, I'm doing it very quickly, 4 minus 9 by 2 is minus 1 by 2, 7 minus 15 by 2 is also minus 1 by 2. Minus 1 by 2 will cancel and we'll get y equals 1. Okay, so notice this is going towards the unique solution direction, and this will imply, 2x plus 3 into 1 equals 5, and that is x equals 1. Okay, so you got a unique solution. I will let you do the checking yourself, 1 comma 1. Okay, it's just simple practice. You can practice for this any number of times. You might have done it numerous times earlier as well. Easy situation. The next problem is 4x plus 8y is 7 and 2x plus 4y is 5. Let's try that. I think I've cooked this up so that you'll get a different type of solution here. 4x plus 8y equals 7, 2x plus 4y equals 5. Okay, is that correct? Okay, you can also try all these things graphically. Okay, you can go and plot these lines and you'll see they will intersect at this one point. Okay. You can plot this also, but let's see how this is going to go. This has got a1 equals 4, a2 equals 2, and then I've got to do 2 minus 2 by 4 times 1, 2 minus half into 1, and that will be 2x plus 4y minus 1 by 2, right? So anyway, let me just write it laboriously. 4x plus 8y equals 5 minus 2 by 4 times 7. So maybe I should write it more clearly. Okay, so you see that the 2 will cancel here. I'm going to get 4 minus 4. Oh my god, look at that. 4 minus 4. Did I get that right? Maybe I should show you how that happened. 4 minus 2 by 4 times 8 times y equals 5 minus 14. So again 7 by 2. Okay, And guess what you get here? You get 0 here, right? So 2 by 4 into 8 is 4 minus 4, that's 0. And guess what you get here? 3 by 2. Okay, this is a contradiction, right? So anytime you have a contradiction like this, you're not going to get a solution. There's no solution. Okay, remember, when there's no solution, this actually is a parallel line, right? These two lines are parallel. You can see, this line has been multiplied by 2, but instead of 10 here, they put 7. So it's like it's going to move a little bit away. So this is these two lines are parallel. You can plot it on Desmos and check, and there's no solution here. So this is a case where through the elimination, we saw that we got a contradiction, and when you get a contradiction, you know that there's no solution. Okay, so this is how through the elimination you find out what type of solution is it. You keep solving, assuming you will get something, and if there is no solution, you will get a contradiction, and that contradiction comes in this way. Okay, so pay attention to that. And the next problem and the last problem we're doing in this lecture is 2x plus 3y equals 5 and 4x plus 6y equals 10. Let's try that. So here again, let's try and eliminate 2 minus 4 by 2 times 1. Okay, so I should say what 1 is and what 2 is. I forgot to say that here as well. Equation 1 and equation 2. So if you do this, you're going to get 4x plus 6y. I'm just doing it laboriously. I guess you can do it much faster than me. 2x plus 3y equals 10 minus 4 by 2 times 5. So here another interesting thing will happen. X will cancel. Okay. And guess what happens to y? Y minus 4 by 2 times 3 times y, and this is 10 minus 10. So guess what you get here? It's 2, 4 by 2 is 2, 2 times 3 is 6. You get 0 equals 0, right? There's no need to solve for any value of y. So whenever you have a 0 equal to 0 type situation, you will end up in an infinitely many solution case. So these two straight lines are actually not two different straight lines, they're the same straight line. You divide this second straight line by 2, you get the first one, right? So it's obvious here. So anytime you have infinitely many situations, solution type of situation, you will end up after elimination or during the elimination process with a 0 equals 0 type of equation. So which means, one variable is irrelevant in this problem. I can put any value for y, I will get a unique solution for x, right? So I'm going to get that. So second equation doesn't matter at all. Okay, so only the first equation matters. Okay, so let me just write that down. Any y, okay, y can be anything. Let's say y equals some u. U is any real number. And what is x? You can put it into the first equation and solve for x. So 2x plus u plus 3u equals 5. Push this to this side. X is 5 minus 3u by 2. Okay, so what is the set of all solutions? It's basically one straight line, 2x plus 3y equals 5. Another way to write it is 5 minus 3u by 2, comma u, and u is in the real line. Okay, so this is the same as the straight line 2x plus 3y equals 5. So this is the line. Notice how differently I've written it. This is called a parametrized form for the straight line. Okay, I've put y as u, is some parameter, real number, any real number u you can take, and then x will become 5 minus 3u by 2, so that this equation is solved, right? So this is a parametrized form for the same straight line, 2x plus 3y equals 5. Okay, so this is this form of writing the infinitely many solutions. Whenever you get it, it's actually just the straight line, but you will see that this form of writing it is very important. Later on, when we generalize, we'll see this. And this form, this way in which when there is no solution, you get a contradiction is always true. It will happen. And when you have a unique solution after elimination, you will just find one value for each of the variables. Okay, hopefully these solutions showed you the various different types of solution possible. Pay attention to the last one and how you have to write the parameterized form for the straight line in some way to characterize all the solutions. And that also is a good technique to learn, right? How do you write this? At least in this particular case, it's easy. As we go to larger number of equations, it will be a little bit more tricky, but you can write it nevertheless. Okay. This is the end of this lecture. Hopefully it was good learning how to solve two equations in two variables. In the ensuing lectures, we'll slowly start building on this and looking at bigger sets of equations. Thank you very much.